This is a video from the Exam 1 Review Part 1. Let's take a look at Problem 1. Let V equal the set of all vectors AB in R2 such that B equals 3A plus 1. So notice the first component is A. If I take the first component, multiply by 3, and add 1, I'm going to get B back. Assume that vector addition and scalar multiplication are the standard operations on the set. Is V a vector space? The answer is no. Now, if I look at the vector where the first component is 2 and the second component is 3 times 2 plus 1, that vector belongs to V. And the vector in which the first component is 3 and the second component is 3 times 3 plus 1, that also belongs to V. But when we add these two vectors up, this is equal to the vector 2, 7 plus the vector 3, 10. But that's equal to the vector 2 plus 3, right? That's the first component. And the second component is 7 plus 10. But that's equal to the vector 5, 17. Notice, the vector 5, 17 belongs to R2, but if I take 3 times 5 and add 1, I don't get 17. So the vector 5, 17 doesn't belong to V. And let me also add, if we take 2, 7 and 3, 10 and add them, right, 2, 7 plus 3, 10, and add them up, that sum doesn't belong to V. And so therefore V is not closed under addition, and that axiom fails. Now, we can also check for scalar multiplication. 2, 7 belongs to V as we established above. Does 4 times the vector 2, 7 belong to V? The answer is no. 4 times 2, 7 is 4 times the vector 2, 7 is equal to the vector 8, 28, right? Regular scalar multiplication is defined here. Now, 8, 28, that vector is in R2, but 3 times 8 plus 1 doesn't equal 28. So the vector 8, 28 doesn't belong to V, and so 4 times the vector 2, 7 doesn't belong to V. And so V is not closed under scalar multiplication. And so those are two axioms that fail right off the bat. And the question I would have for you all, are there any others? Okay. And that's a good question. Can you find another axiom that won't work? Let's take a look at 2. Let V equal the set of vectors AB in R2 with scalar multiplication defined by k times the vector AB is equal to the vector KAB. So notice I took the first component and multiplied it by k and left B alone. Is V a vector space? The answer is no, interestingly. Now, the vector 2, 3 does belong to V since 2, 3, that vector is in R2. Now, what I did was I took scalars negative 5 and positive 7, okay? So I took the quantity negative 5 plus 7 and multiplied it by 2, 3, that vector. But negative 5 plus 7 is equal to 2. So this is 2 times the vector 2, 3. But the way scalar multiplication works, I'm going to take 2 times the first component to get 4, and then 3 gets left alone. So we get the vector 4, 3. And if we take negative 5 times the vector 2, 3 and add it to 7 times the vector 2, 3, this is equal to negative 10, 3, right? That vector, plus the vector 14, 3, right? But that's equal to the vector 4, 6, right? Because 3 plus 3 is 6. Regular vector addition applies. And then negative 10 plus 14 is equal to 4. That is not equal to the vector 4, 3. And so therefore, negative 5 times the vector 2, 3 plus 7 times the vector 2, 3 is not equal to negative 5 plus 7 times the vector 2, 3. So axiom 8 fails, and so therefore V is not a vector space. And again, the question I have for you is, are there any other axioms that will not work? And that'll do it for this video for the exam 2 review part 1, and we looked at problems 1 and 2. Okay, thank you.